Hello students, welcome to the channel. In our continuing series Basics Explained, we look at the fundamental concepts of various topics that you are likely to see on the SAT and the ACT. Today we look at algebraic graphs. Why are we calling them algebraic graphs? Because on the SAT math section, you get two kinds of graphs. One that tests your knowledge of algebraic functions. So graphs, that are wavy and that ask you about x-intercepts, y-intercepts, and all of that. So that's what we are going to discuss in this video. And the other are graphs which are related to arithmetic, graphs that have histograms, graphs that have bar charts, etc. So that's part of problem solving and data analysis, and that will be in another video. Today, we'll focus on graphs that you're likely to see on algebra questions. So let's begin. First, let's understand the concept of a function as represented on a graph and what do the intercepts for this function stand for. So if you look at this function here, I notice that this function touches the x-axis at -1, at 1, and at 3. These are called the roots or the solutions of the function, right? Remember, the word roots here is the same as the word solutions for the function, right? Which is to say that if I were to plot this, let's say this is the function f of x, and this is x, then this function would take a value 0 when x is -1, when x is 1, and when x is 3. That is, I could write this as some constant a times x plus 1, x minus 1, and x minus 3. X plus 1 corresponds to the x-intercept of -1, x minus 1 corresponds to the x-intercept of 1, and x minus 3 corresponds to the x-intercept of 3. So here, the factors x plus 1, x minus 1, and x minus 3 are directly related to the x-intercepts of the function. Okay, let's move on. So I have another function here, and this function has x-intercepts at -2.21, 0.54, and 1.68, right? Because it meets at these 3 points, these 3 points are known as the real roots of the function. The real roots of the function are the points where the graph meets the x-axis. So if this was fx and this was x, if this was a degree 3 function, if it was a degree 3 function, I would say that all its roots are real because I can see that here the graph has 3 real roots. But let's say fx was a degree 5 function, then I would say that it has 3 real roots and 2 complex roots. Why would it have 2 complex roots? Because when the coefficients of a function are real, the complex roots will always appear in pairs, right? One would be the complement of the other with the sign of the imaginary part changed. So the basic point to remember is that wherever the graph cuts the x-axis constitutes a real root of the function. So what about the y-intercept? The y-intercept is the point where the graph meets the y-axis. So let's say I have any polynomial written in the expanded form, ax cubed plus bx squared plus cx plus d. So d here, the constant term is always the y-intercept because when you put x equal to 0, the function effectively becomes d. So d is the y-intercept. Okay. Now, another important concept to remember is the concept of repeated roots. What do I mean by a repeated root? So consider 2 parabolas, one representing the graph of y is equal to x minus 1 and x minus 2. So this is a parabola with 2 distinct roots, x equal to 1 and x equal to 2. And the other is x minus 1 whole squared, which is a parabola with only 1 root that is repeated. So you notice here that for a repeated root, the graph is merely tangential to the axis. It doesn't cross the axis, right? So this is the graph for x minus 1, the whole square. And what is the property of repeated roots? The property of repeated root is that the discriminant of the quadratic should be 0. So let's verify that. My quadratic is x squared minus 2x plus 1. So the discriminant will be b squared minus 4ac. b is minus 2, so 4 minus 4 into 1 into 1. And I can see that this is 0. So when the discriminant of a quadratic is 0, it would indicate a repeated real root. And that real root will touch, the graph will touch the x-axis, not cross. What about here? When the roots are distinct, the discriminant should be greater than 0. And fx here is x squared minus 3x plus 2, right? So discriminant is b squared minus 4ac, which is 1. So we see that the discriminant is positive. What would happen if the graph looked like this? Here, the graph does not have any real roots because it does not cross the x-axis. And so the discriminant would be negative. Okay, so let's understand or rather work on these concepts with some sample questions. The graph of y is equal to fx is shown where a, b, c, and d are constants. What is the value of f0? So f0 is the value of the graph when x is 0, which means that we have been asked to find the y-intercept. And I can see that the y-intercept of this graph is option B, right? A, C, and D are all x-intercepts, right? So here my answer is option B. Question 2, the graph of the function f is shown in the xy plane above, where y is equal to fx. Which of the following functions could define f? So I'll first find the intercepts. I have an intercept as negative 3, so x plus 3 is a factor. At negative 1, so x plus 1 is a factor. And at 2, so x minus 2 is a factor, right? Furthermore, I see that at negative 1 and 2, the graph is tangential to the x-axis. It is returning from the axis, not crossing. So I would put a square term for x plus 1 and for x minus 2. So the right answer would be fx is equal to x plus 3 times x plus 1 squared times x minus 2 squared, option C. Okay, question 3. Which of the following functions could represent the graph shown? So the first thing I notice is that I can see 3 intercepts. So that means my function has to be a cubic function. It clearly has 3 real roots. So I can cancel A and I can cancel C because they are quadratic. Now, if I look at option B, I can write it as x times x squared plus 6x plus 8, which is x times x plus 2 into x plus 4. So that is option B. And option D gives me x times x squared minus 6x plus 8, which is x times x minus 2 into x minus 4. So option B, my x-intercepts should be 0, negative 2, and negative 4. And option D, my x-intercept should be 0, 2, and 4. And I can see that all the x-intercepts to the left of 0 on this graph, that is to say that all the x-intercepts are negative. It's on the negative x-axis, which means the right answer should be option B, not option D. Question 4, which of the following graphs appears to represent a polynomial function with a double zero or repeated root? Double zero or repeated root, as we have said, is represented on the graph when the graph turns from the x-axis. And I can clearly see that in option D, there seems to be a repeated root here. So let's say this is -1. So when I write down this as a polynomial, I would have a term like x plus 1, the whole squared, because that's a repeated root there. Here I see 3 distinct roots. Here I see 2 distinct roots. And here there are no real roots, right? So the only option with a repeated root and a distinct root here is option D. So this was a very basic explainer on how to approach algebraic graph questions on SAT and ACT. If you found this useful and would like more such videos, let me know in the comments section. Hit like and subscribe to the channel and come back for more content. I'll see you guys soon. Take care. Bye-bye.